Hello and welcome to this video on rockets. In this video I'll go through the general structure of a rocket and then we'll derive the rocket equation. As you can see on the screen, this is a simple rocket. It's got two main parts to it, the combustion chamber and the nozzle. The nozzle is a very important part of the rocket. It's connected to the combustion chamber and it's a section where it converges and then it diverges again. The exit plane is labelled and so is the throat of the nozzle. How a rocket works is in the combustion chamber, the propellant is ignited. This produces exhausts, and as it goes through the nozzle, this exhaust is compressed. The compression reaches a maximum at the throat, and on passing out the throat, it's allowed to expand very rapidly, and it's this rapid expansion that causes the exhaust velocity to have such a high velocity. So the nozzle allows you to accelerate the gas molecules. Exhaust is expelled from the rocket, and that produces a thrust. It's that thrust that increases its linear momentum. This acts through its center of mass. Also labelled on the diagram, you've got a component of external force. This could be aerodynamic drag, pressure or gravity, and these are forces that will act against the exhaust, which could reduce thrust. The ambient pressure is the pressure outside of the rocket. Now when you go to space, it's a vacuum, so the ambient pressure goes to zero. Now we'll have a look at the rocket equation itself. Before we derive the rocket equation, I'm just going to explain a little bit about the equation and why it's important. So, the rocket equation has a few names that I'm just going to let you know about just to be aware of. So it can be called don't quote me on this because I don't speak Russian, so I'm sorry if I butcher the pronunciation. But it goes by Tsiolkovsky rocket equation, the classical rocket equation, and the ideal rocket equation. To be honest, most people just call it the rocket equation, and it's usually okay, and people know what you're talking about. Now there are a few ways that you can derive it. You can use the parameters of the rocket, which I will do in a later video once you're more familiar with rockets and their parameters. You can derive it that way, but in this video I'm going to be using Newton's laws and momentum exchange to derive the rocket equation. So, what does the rocket equation tell us? Well, it's basically an equation that describes the motion of an object, a vehicle, a system that applies acceleration to itself by thrust, and this thrust is usually imparted by expelling some sort of weight or some sort of mass at high velocity. The rocket equation doesn't just apply to rockets, it applies to any sort of system that applies acceleration to itself, but the most famous example of that type of system is a rocket, hence why it's applied to rockets, and we know it as the rocket equation. So, let's derive it. I'm going to begin just with these two diagrams. So I've got the rocket at time equals 0, where you can see there hasn't been any expulsion of mass yet, or the propellant hasn't been expelled yet. The rocket has a mass, the propellant has a mass, delta m, and the rocket also has a velocity v. Now at a time later, at times delta t, the rocket still has a mass, but you can see that the propellant or the exhaust has been expelled from the rocket, so it's lost mass, and that's been expelled with a velocity ve. I'm just going to write this as a minus the velocity of the exhaust in the rocket's frame. It will come in handy later. Using Newton's second law, we know that force is equal to a change in momentum over time. So if we expand that out, that's the momentum at the end, or the final momentum, minus the initial momentum over some time. Moving to the right of the screen, I'm just going to write out the values for the momentum for t is 0 and t is delta t. So the initial momentum, pi, is when t is 0. Momentum, remember, is mass times velocity. So the momentum at t is 0, the total momentum of the system. Well, the mass is the mass of the rocket plus the mass of the propellant because it hasn't been expelled yet. And the velocity is just v. Momentum at the end, the final one, final momentum. Well, you've got the momentum of the rocket and the momentum of the expelled propellant. The total momentum will be the sum of both of those. So starting with the momentum of the rocket, it's got rid of the propellant mass, so the mass is just m, but the velocity has changed. So you've got v plus delta v. And the momentum of the propellant is delta m v e. Now I'm just going to rewrite the v at the end. Okay, now we've got these expressions. Delta p. I'm going to expand the brackets as well. So it's the final v plus m delta v plus delta m v minus delta m exhaust velocity minus mv minus delta m v. So we can cancel certain things. So these cancel and these two cancel. That means we're left with m delta v minus delta m exhaust velocity. One thing I will mention is because the mass is being expelled, there's a reduction in mass. So here I'm going to make the mass expelled minus. So this will change the above expression. Like that. Okay, using this, if we go back to Newton, we can put this in and we end up with the sum of the forces is mass dv by dt plus exhaust velocity dm by dt. We're going to assume that the resultant force is 0. So, like, momentum has been conserved. M dv by dt is negative exhaust velocity dm by dt. Integrate both sides with respect to time. You end up with mass times velocity between the initial and final Now divide the m so you end up with just the velocity on the left hand side. And you can integrate that with respect to mass. So this just becomes delta v. It's just the difference between the final and the initial velocities, it's just delta v. And on the right hand side, you've still got the negative, and it's 1 over x, so it's just ln x, ln m between final and initials. Using logarithm rules, expand it out, so it's mass final minus mass initial. So minus and minus just make a plus. Ln mo over mf, where mo is just the mass of the rocket initially, so the mass when time is 0, so nothing has been expelled yet, and mf is the mass after all of the expulsion of the propellant. To make it nicer, I'm going to express mf using mo. So like I say, mo is the mass of the rocket before anything's been expelled, so that will be equal to the mass at the end, mass final, plus the mass that's been expelled. Rearrange that to make mf the subject, and then just substitute that into the equation. I'm going to write this in a different colour because this is the final equation. That is the rocket equation, and just to go through, just so you know what each term is, delta v is the change in velocity, ve is the velocity of the exhaust, ln being natural log, mo is the mass of the rocket before anything is expelled, and me is the mass that has been expelled. Now remember what I was saying before, this equation assumes that there is no external forces acting on it, and it also assumes that the exhaust is being expelled into a vacuum. But as we know, when we set off a rocket from Earth, we've got to go through the atmosphere, and as we're going through the atmosphere, the exhaust basically has to work against the atmosphere, which can reduce thrust. So this equation doesn't account for that, but as soon as you hit the vacuum of space, you should be good because you shouldn't have that ambient pressure there to work against the thrust. This has been a video on an introduction of rockets. Showed you a basic rocket, some important features of it, and then we derived the rocket equation.